Welcome back to the course on superconductivity. Today we're going to talk about quench and normal zone propagation velocity. We'll first define what a quench is, describe the normal zone propagation velocity, and finish by showing how the experiments are usually done. We'll use these variables in the equations, so feel free to pause the video and take a screenshot of this table. First of all, as described by Bob Walsh, an engineer of the National Magnet Laboratory, quench is a technical description for a pretty dramatic event. It means that the magnet crashed, and it will be a while before we can use it again. In this video here, you can see the magnet container filled with helium. We can see the helium expelled from the container due to the overpressure. In a more physical way, you can see a quench as a part of the magnet that becomes, for some reason, normal. This means that the high current that was flowing in the superconducting state is going to go over a normal zone, at which a lot of Joule heating will occur. When working with wet magnets, this heat will vaporize the cryogen, hence, we usually see these kinds of big clouds of helium expelled from the container. An important property is the normal zone propagation velocity. After the quench occurs, the Joule heating at the normal zone will heat up the surrounding cable, eventually causing the neighboring area to become normal as well. Taking at a time t the position of the boundary between the normal region and the superconducting region and taking it after a small time delta t, we define the NZPV as the position difference L divided by the amount of time we waited delta t. Also, the velocity is not the same depending on the direction. If we measure it in the direction of the winding, called longitudinal velocity, we usually get a faster NZPV than if we measure it in the turn-to-turn direction, called transverse velocity. Here, we will derive a formula to get an order of magnitude of the longitudinal NZPV. The main assumptions are that the system is adiabatic. We will first consider that the conductor is only made of superconductor, and the propagation is in one dimension. Taking back the equation from chapter 5.1.9 and removing some terms according to our assumptions, we get two equations, one with the Joule heating and conduction term for the normal region and one with only the conduction term in the superconducting region. At first, we used x as an absolute coordinate, but what is interesting for us is the moving boundary that we will call z. Z is defined so that at any time t, z equals 0 at the normal superconducting boundary. This also introduces the longitudinal NZPV, which here is considered constant. We will also use the following boundary conditions. At z very large, we will consider that we are at the operating temperature. At the boundary, the conduction terms must be equal, and at the boundary the temperatures must be equal. Here we noted Tt to denote transition temperature, whose definition can change with the case. For a normal conductor that has a matrix, the current sharing temperature can be used, or a mix of the critical temperature with the current sharing temperature may be used. We will consider the thermal properties of the material's constant versus temperature and the second derivative of the temperature in the normal zone close to zero. These assumptions individually don't look strong, but in reality, that means that we ignore totally the conduction term in the normal zone. Also, keep in mind that the thermal properties of HTS vary a lot between their operating temperature and their transition temperature, so this assumption is usually used for LTS. Now, we can just solve the superconducting region's equation using the temperature boundary conditions. Now, using the boundary condition linking the conduction terms, we can link the previously solved equation with the equation in the normal region. Moving the terms around, we can get an equation giving the longitudinal NZPV. However, we started by considering a conductor made of only superconducting materials. To get an equation that takes into account the matrix, we can consider the matrix being the biggest contributor to the thermal properties and consider that the Joule dissipation occurs only in the matrix. Now, we have an equation to get the longitudinal NZPV for a normal superconducting wire. Because of all the assumptions we made, we might think that this equation is not very accurate, especially for HTS, but it was verified experimentally that this equation gives reasonable orders of magnitude for LTS and HTS wires. With the longitudinal velocity, we can determine also the transverse velocity using this formula. To measure the longitudinal NZPV, a heater is used to start the quench at one point of the wire with DC current and some voltage taps are fixed at known distances from the heater. Considering that the voltage taps of V1 are at L1 distance from each other and that V1 reaches its maximum after a time delta T1, we can define the longitudinal NZPV as L1 divided by delta T1. Here's a table with some longitudinal NZPV values for several superconducting wires. The main thing that we see here is that usually the NZPV of the LTS is much faster than for the HTS wire. Here we see some experimental results for YBCO tapes. The main thing to remember from this slide is that the NZPV increases as the DC current increases. On the right-hand side graph, we can see the almost linear dependence of the NZPV on the applied current. Now that we've defined the NZPV and seen its properties, we can understand the difference between a quench in an LTS magnet and an HTS one. As we said before, a quench is when a part of the magnet becomes normal. The current inside the magnet being high, the normal zone might create so much Joule heating that the normal zone will propagate throughout the magnet. For LTS magnets, we usually have a very fast NZPV, so the quench happens in a short amount of time and causes a big and sharp voltage jump. This means that it is relatively easy to know when a quench occurs in an LTS. However, for HTS, the NZPV is very slow, and the small voltage variation when a quench occurs makes it very hard to detect. Currently, detecting quenches in HTS magnets is a major problem. You might take a look at this paper that references the currently existing methods to detect a quench in HTS magnets. To conclude, by definition, a quench is when a part of a magnet becomes normal. The normal zone propagation velocity, NZPV, is the speed at which the quenched part, normal part, expands in the magnet. Quenches can and will deal heavy damage to a magnet. That is why making preparations during the design phase to prevent permanent damage is so important.